Hello, so in this lab you're going to do the unexpected reaction of 2,3-dimethyl 2,3-butane-diol, which has this structure over here, where you have a vicinal, diol, or neighboring alcohols. In this we will also use sulfuric acid as a catalyst to produce the quote-unquote unexpected product. Make sure that you read the procedure and complete your pre-lab assignment after watching this video. Before the reaction, let's take a quick review on what usually occurs when alcohols are in the presence of any strong acid. You will have an acid-catalyzed dehydration, or basically you're eliminating water, which is in this step right here. Pause the video for a bit to look at this mechanism. So in the first step, the alcohol is going to be pronated, so then it can leave as water, which is actually a good leaving group. And since this is a secondary alcohol, and normally with secondary tertiary alcohols, it can undergo SN1 or E1 mechanism to form an unstable carbocation intermediate. And because carbocations are susceptible for rearrangement, what can happen is a hydride or methyl shift to get to a more stable carbocation. So in this example, you have a hydride shift forming the more stable tertiary carbocation. And because in the first place we had water as the conjugate base, the water is going to act as the base to form the double bond, which is the Zaitsev product. Okay, so now what happens when we use strong acids where their conjugate bases are actually nucleophilic, meaning it can attack the carbon where the carbocation was? Something like hydrochloric acid or HCl or HBr can do this. So in the first step, the alcohol again is going to be pronated in acidic conditions. This is the conjugate base. Water will leave and produce carbocations. But instead of elimination, the chloride conjugate base is going to attack or attach to the carbocation and substitute that water that just left. So what we know about carbocations and carbocation stability is going to determine the product that is formed. And we know that tertiary carbocations are more stable than secondary and primary carbocations. But what if we have a double bond next to that carbocation? Well, if we have a double bond here, it's actually going to produce a resonance structure. And because this is now resonance stabilized, this is going to be more stable than the tertiary carbocation. Now, for example, out of these two structures, which is more stable? Well, they are both tertiary carbocations. In the first one, we have a methyl group, and on the other, we have a hydroxyl group. So the methyl group can donate electron density to the carbocation, stabilizing it. But while oxygen can pull electron density away, destabilizing it, the stabilizing factor is actually going to be its resonance structure. So this alcohol is going to donate a pair of electrons, and as shown here, you're going to have a resonance structure where the carbon now has a neutral charge, stabilizing it. So this is actually the more stable tertiary carbocation. And in this lab, we will be investigating what happens to diols, and basically two alcohol groups, in the presence of acid catalyst. And this reaction actually occurs with a variety of fully substituted diols. And in this lab, you will basically determine how this reaction occurs and determine the mechanism. To run the reaction, first you will want to assemble your distillation apparatus. You want to set the blue lab jack under so that you're ready to mount the stir plate and also the heating mantle. Then into a round bottom flask, you will weigh out 12 millimoles of the diol starting material. Then you want to carefully add the sulfuric acid solution, which is the acid catalyst, and then place your round bottom flask connected to the distillation setup. Tip number 1 is to always ask your TA and make sure that you ask them to check your setup before you can proceed to start heating. Tip number 2, you want to turn on the steering plate, but you don't want to turn on the heat on the steering plate. Instead, you want to use the variable controller and then you can then ask your TA the setting at which to set the percentage. You will then want to make sure that you keep an eye on the thermometer and record the temperature once you start collecting distillate. One last thing is that you don't want to distill to dryness and look at your round bottom flask so that nothing burns. Once you're done, you want to turn off the controller and also adjust the lab jack and set it down so that your round bottom flask stops heating. Okay, so if you collected your distillate and found that you had 2 layers of liquid, you're going to want to separate your product, which is in the organic layer. So what you will do is transfer all of the distillate to a separatory funnel and then see if there's a clear separation between the 2 layers. If not, you can always increase the volume of the total liquid by adding more water or adding more brine. Then you will want to remove the first water layer, keep the organic layer, and then wash this with saturated sodium chloride solution. You want to wash this with brine for a total of 2 times, or the total collected organic layer with your product should be dried with anhydrous sodium sulfate. Then you want to remove the sodium sulfate by decanting this, and then you want to decant your product into a pre-weighed round bottom flask so that then you can weigh this. Finally, you will need to weigh the liquid or your product to be able to calculate the percent yield, and then you will also take an IR spectrum and an NMR spectrum for both the starting material and the product that you've isolated. Just a little tip, before you take the IR and the NMR, I would suggest to rationalize the mechanism by going back to the beginning of this video and basically predicting what the mechanism should be based on the stability of the intermediates, and then that should give you the structure of the quote-unquote unexpected product.